what I'd like to talk about for the next 10-15 minutes or so is what are these challenges? How do we deal with them? What makes data science in the world of transport so interesting? And ultimately, how do we make our own lives easier as data scientists, and how do we make our clients' lives easier as Dynniq, a solutions provider, by getting back from that to something which at least looks on the surface more like that? Okay, so we're going to start by doing a bit of data analysis right here, right now. And you may not believe me that you are all really good at data analysis. And when I say you, I don't just mean those of you who are a bit weird and those of you who are going to out your pocket calculators. I mean all of you. And you are going to do this data analysis right now, whether you like it or not. Still don't believe me? Here comes the data. There you go. It's a lion. But you all knew that, right? You knew it was a lion. And in recognizing that series of little colored squares as a lion, you've already beaten most computer image recognition algorithms. And you've done that without even thinking about it. But let's imagine now we're not at Traffex, we're not staring at a picture of a lion on a screen. We're out in the wilds of Africa, and that is what we're seeing with our eyes, right in front of us. We're going to be doing some pretty rapid data analysis, I would suggest. And it's going to go something like this. Lion. What else comes into my mind immediately after lion? Well, these are definitely pretty scary things. They eat people, I'm pretty certain of that. I've seen that in the news. This is an angry face. This is not a pleasant, happy, smiley face. This is definitely an angry thing. And it definitely looks like it's going to bite me. I've seen things biting things before, and this is what things that bite things look like. Action? Run away. Or at least try to. So there we go. Journey finished, data, insight, action, done, and you haven't even thought about it yet. Let's try it again then. Let's try a slightly harder one. I'm going to ask you to predict the future now. So I'm going to show you a picture and ask you what happened next. Ready? Let's go. There's a picture. What happened next? I'm going to make it slightly easier by giving you two options. Option A, he went for a ride. Option B, he went for a ride and crashed his bike on a fast corner. Now, I guarantee you that some of you were thinking option B before I even put those up. You saw that picture of that motorcycle, and into your head came the idea of having an accident. Now I've put those options up, some of you are still thinking option B. You're thinking option B despite the fact that it's logically impossible. You cannot go for a ride and crash your bike without first going for a ride. A completely contains option B. And I can still guarantee you that even after I've told you that, many of you are still thinking, yeah, but it is B, isn't it? It's obviously B. So we've seen one example there where you could subconsciously make that whole journey, data, insight, action, and get it right. We've seen one example where you subconsciously make the journey but get it wrong. There are plenty of other examples where you can't make that journey subconsciously at all. Let's think logic puzzles. If I give you a logic puzzle, nothing intuitively pops to mind as the answer. If I give you a set of IKEA instructions, you don't instinctively know how to assemble the bookcase to stop and read the instructions. And that's what gives us an advantage as human beings. We have the capability of rational thought. We can stop and think about things. We don't have to go purely on our first instinct. And similarly, we can share our knowledge with other people. We have the ability to communicate, write, talk, use email, whatever it might be. So back to this journey. How does this ability to think rationally, to take time to share our thoughts with other people, actually manifest itself in the world of predictive analytics, the world of data, insight, action? Well, it manifests itself in one spectacularly useful field of mathematics, and that is everyone's favorite field of mathematics, statistics. Okay, now much like with the motorcycle, I can guarantee you that when you eventually saw that word on the screen after something of a wait, you thought, statistics? Oh, what? This is just rubbish. When you think of statistics, you think of this kind of thing. 79% of engineers agreed that Scoot TMS made their junctions feel young again. That's statistics, isn't it? That's all that statistics is. It's some kind of bump that advertisers make up. No, it's not. And while this statement is entirely true, it is nowhere close to covering the range of the power of statistics as a methodology. So let's take a little look at at a statistical problem. This is what you call an inference problem. This is where we're trying to use some data, some observations, to understand what's really going on. We're recreating reality from a limited set of observations. And such a problem that you might be well familiar with, if you're familiar with Dynniq's products, is Scoot. Scoot is a signal control algorithm, and to control the signals, it needs to know what's going on around the signals. And in reality, we know that there are definitely roads, there are definitely signals, there are definitely vehicles on those roads queuing up something like this, and there's no real ambiguity there. However, that's not what we observe. We don't have this bird's eye view of the junction watching everything that's going on. All we're observing is the results coming from a set of detectors. There you go, you can see them lightly there in orange. So you've got a set of detectors. That's all we've got coming in. However, we also know static data. We know the road layout. We've got an understanding of dynamics. We understand that vehicles can't move through each other. They can't leap off the road sideways, or at least not in a way that's conducive to continuing their journey. And they tend to follow each other, move away when the lights are green, etc. And that is sufficient to recreate reality for the sake of running Scoot. However, let's take a pause there and consider a quote which I have borrowed and failed to attribute, unfortunately, so I have to Google it to find out who it should be attributed to. All models are wrong, but some are useful. Okay, so am I saying that Scoot's wrong? Well, if by wrong you mean incomplete, yes. Scoot is not going to tell me anything about the lives of those people in the car. It's not going to tell me where they're going after they leave that junction, or where they came from before they got there. It's not telling me what economic contribution they're making to the local area. It's not telling me any of those things. But I don't need it to tell me those things in order to decide when the lights go red, amber, and green. So it is wrong in the sense that it's incomplete, but it's useful because it gets the job done. So let's take a little bit more of a look at how to be wrong. So our little junction is likely part of a wider network. And if we want to understand what's going on in that wider network, we might need to pull in multiple data sources. We've already got our loops, we've got our static data, we know what the road's like, we can read that from a road map. We still understand the dynamics of vehicles, they remain largely unchanged. We might throw in some ANPR to give us journey times along this main stretch of road. We might throw in some floating vehicle data whereby a subset of vehicles tells us where they are every second, 10 seconds, whatever it might be. However, in the sense of wrong being incomplete, all these data sources are wrong. None of them tell us the complete picture. So, for example, those loops, if I wanted to know the traffic flow at exactly the site where the loop is, then could that be wrong? Well, yeah, it could be wrong if the loop's not set up right, if it's calibrated poorly. However, if it's calibrated well, there's not that much scope for it to be wrong, and not by an awful lot. However, if I wanted to know the flow along that whole horizontal road down the middle from just one of those loops, then there's more potential for it to be wrong, because we could have much higher flow on the left side than the right side if there's a lot of traffic turning off at the junction. If I want to know the flow in 5-second increments, then that creates another way to be wrong, because the flow in any 5-second increment over the loop could be quite different from the flow in a 5-second increment further down the road. So by understanding how I can be wrong, it also tells me how right I am. Similarly with all these other data sources, I'm not going to go through them all one by one because I would bore you all to tears, but I can do that afterwards if you'd like. But they can all be wrong in different ways, and you can use each of them to help quantify how wrong the others are. And this is where you start to move into more complex inferential statistics. You can understand the error of each source by looking at the other sources and ultimately build up a single best estimate of what's going on here. And importantly, understand how wrong that overall best estimate is. However, even after you've done that, and that is genuinely a complex problem, there are maths professors that have told me this is a complex problem, and I'm not just going crazy. It's still wrong in the sense of being incomplete. Where do the vehicles go when they stop? We've created a network in which vehicles move continuously and never stop. This is ludicrous. how much noise these vehicles are making. This is important, isn't it, to the people nearby? How much noise the vehicles are making? Well, they don't make any noise. There's not even any air in this model, as far as I'm aware. Where does the exhaust go? Well, presumably in that missing air. What's in the white spaces? There are definitely things between roads. I'm pretty certain there are things between roads. There are buildings, there are houses, there are industrial estates, workplaces, retail areas. Surely that's important somewhere. What about the people? There aren't any people in this model. Our base unit of this model is vehicles and roads. Where have the people gone? How much coffee will the people buy? And that may not be important to running Scoot, but it's important to running a coffee shop. Are the people happy before or after they get their coffee? I don't know. This model doesn't tell us. Do we need it to tell us? Depends what you want to know. So, that brings us to almost the end of the presentation. Looked at how to be wrong. How to be wrong, step one, accept it is okay to be wrong. All models are wrong. All estimates are fundamentally incomplete. If you could predict everything that would happen in the entire world, you would have just created a parallel dimension. But the important thing is to understand, how wrong am I? How likely am I to be wrong, and by how much? And most importantly, does it matter? If I don't know if people arriving at a Scoot signal want coffee, it's completely inconsequential. If I don't know if someone's arriving at a Scoot signal, then it is quite consequential because the signal could be set wrong. So this brings us to the end of our data insight action journey. The action all comes down to understanding, does it matter for this action that I don't know X, Y, and Z? How well do I need to know them? However, there's one further complication to this. We started off at the beginning talking about humans, motorcyclists and lions. We drifted into numbers, into abstraction in the middle. However, I have to remember that at both ends of this chain, there are humans, particularly in the transport industry. All this data we're talking about is generated by people doing things, people exhibiting human behavior. It goes through the engine of insight, statistics, etc. And ultimately, your actions have to be potentially implemented by humans, certainly implemented on humans, and you have to take that into account as well the whole way through. If you fall into the trap of ignoring the humans and just assuming completely logical, rational behavior of all these agents, maybe ignoring them altogether and just assuming they're vehicles which have some kind of self-interest, you'll lose a lot of the subtlety there. Humans are fundamentally not rational, and that's okay. We're all fundamentally not rational until we take the time to try and consciously be rational. The mistake is to assume that everyone else is rational and it's just you that's the problem. Very last slide, just a couple of quick example projects for you to maybe spark a bit of further conversation. We're working on 2 projects right now where the human element is particularly important. There's the Flourish project, which is all about connected and autonomous vehicles in Bristol. There's 2 particularly important human elements there. There's the people who are getting in these cooperative and autonomous vehicles. Us and our partners are doing some work around the human-machine interface, which confronts you when you get into that vehicle. And we're also doing a lot of work around how network operators interact with this whole new type of data, this new network operation paradigm. So that's 2 sets of humans right off. EST in Exeter has a slightly wider set of humans. It's basically everyone. We're doing a process whereby we're involving the traveling public in first feeding back about their travel experiences, their behavior, and then co-creation of interventions to improve that experience. So I'll leave that there. Come and chat to me afterwards if anything I've said has piqued your interest. Check out our demos over there. We've got a few bits of predictive analytics going on live. So thank you very much for your attention, and I'll let you get back to your lunch.